how do I see how the recording starts?
The recording has started. You can start. Thanks.
All right. Thank you very much for inviting me to give a talk. So I'll be talking about how hard is it to get a de Sitter space in string theory. So some part of this talk I gave at Sunil Fest and later on in the Indian string meeting, but I will do a little bit more. I'll go beyond what I said there. So if you get bored, you can take a short nap in the beginning, but then hopefully it'll get more interesting as we go along. So in this talk, I will basically summarize some of my older works and some new work that I've started. The talk will be based on the following papers. So this is the paper we first started working in 2014. And then when I went to sabbatical, I worked with Renata and Tim Ross and Eric on Entity3 and de Sitter. And then we started developing this story, and this paper, Quantum Correction and de Sitter Swampland, came along. And then I had two students, Mead and Maxim, who joined me, and then we wrote this paper called de Sitter Vacua in the String Landscape, followed by a paper called How a Four-Dimensional de Sitter Solution Remains Outside the Swampland. I'll talk about more recent paper on coherent states a little bit later. The cast of character, this was my first student, Rhiannon. This is Muhammad. This is Evan. Also, all of these were my former student, and this Radu. And then
just to interrupt 1 second, I think the screen is not changing. Your screen is stuck.
No, we are not seeing anybody except that Taurus.
Oh no.
Yes.
That's much better.
Let's see now what happened. Let's start from beginning.
Also, maybe you can use full screen mode instead of this
full screen mode.
So I use this full screen mode. Now can you see?
Well, it's not on. It's not. We are not seeing the full screen mode. We are seeing it in normal mode.
Oh, that's interesting.
So it's probably not focusing on your full screen window.
Okay.
But maybe it's better if you stay out of full screen mode actually, and just since that doesn't seem to work well, and just make sure that your slides are moving.
Okay. Can you see something now?
Now we can see something. Yes.
Now can you see?
Yes. Yes. We see the references, which we didn't see before.
Okay, great. So I'll not go to the full screen mode. I think that is probably not working very well. So these are the paper I was talking about. This is the paper I started in 2014, followed by all this paper I wrote, and then finally the set of paper I wrote with Maxim and Mead and Radu on de Sitter Vacua and String Landscape. And more recently, I've been working on this de Sitter as a coherent state that I'll probably talk a little bit later. Cast of character, this is my first student, Rhiannon, Muhammad, you may have seen. Evan, who is now in MIT, and Radu, my old collaborators. And this is Eric, whom you probably know, Kalosh, Tony Van Bryan, Tim Ross, who I heard just gave a talk. This is Maxim. And as usual, I never find the picture of Mir, so here is Mir. Since I didn't find any Mir, there you go. Outline of the talk. I'll give a brief introduction to it.
Maybe he should show his video once. You can ask him to show his video face once.
Well, maybe he's around. He's here.
Yeah.
Maybe you can advertise yourself. Oh, there he is.
Yeah.
No-go theorem in the presence of branes and anti-branes. No-go theorem in the presence of Oriental Planes. And the possibility of getting four-dimensional de Sitter solution with higher order quantum corrections. And I'll end with some discussions and conclusion. So as you know, it all started with the work of this gentleman, followed by the joint work of Einstein and de Sitter. which basically led to our modern understanding of accelerating universe as a four-dimensional space-time with positive cosmological constant. Now, question is whether string theory can give rise to a four-dimensional lambda greater than 0 solution. It's easy to show that lambda equal to 0 and lambda less than 0 are abundant in string theory. Part of the reason is because both of them are generally lead to supersymmetric vacua. But as we know that non-supersymmetric vacuum are also possible to construct with lambda equal to 0 and lambda less than 0. On the other hand, if you ask for lambda greater than 0, there is no non-supersymmetric vacua. There are no non-supersymmetric vacua. This is because we cannot construct a closed supersymmetric algebra with lambda greater than 0.
Sorry, you said there are no supersymmetric vacua or no non-supersymmetric vacua?
No, there are no supersymmetric vacua with lambda greater than 0. On the other hand, lambda equal to 0 and lambda less than 0 both have supersymmetric and non-supersymmetric vacua. But this case doesn't seem to have a supersymmetric, although there are some papers I know. But I don't know whether SUSY algebra can close so easily. It turns out that is one of the reasons why it's very hard to construct. It turns out, unfortunately, that's not the only reason. There exists a deeper reason why four-dimensional de Sitter vacua may be difficult to construct in string theory. And we'll argue that with two derivative gravity, it may be impossible to construct a four-dimensional de Sitter solution. Now, why is this the case? And the idea is easy to state in few steps. Consider the following Lagrangian, which contain the kinetic term, and then there is a matter piece over here, in which you can see that this KD is the d-dimensional Newton constant, and RD is the Ricci scalar in d dimension. GD is the determinant of the d-dimensional metric, whose metric components are Gmn. Mn goes from 0 to d minus 1, and I've added a matter Lagrangian L matter to it. Now, this matter Lagrangian can contain global fluxes, scalar fields, local sources, and all kinds of things. And the variation of the action with respect to the metric gives rise to the following equation of motion, which is exactly the Einstein's equation. Now, T is the energy momentum tensor, and Tmn is the energy momentum tensor, and T is the trace given by contracting Gmn with Tmn. Now, let us consider the following metric in d dimension. Let us just divide the metric into a piece which is 3 plus 1 dimension mu nu, and Mn is the remaining part. So mu nu goes from 0 to 3, and Mn goes to 4 to d minus 1. Which means I divided the space into two pieces. One is four-dimensional space-time, and the other is d minus 4. This is the distribution of t, x, y, z, but t is the time. X1, X2, X3, I'll call it as x, y, and z. Now, M d minus 4 can either be a compact or non-compact d minus 4 dimensional manifold, which is described by space-like coordinate xm. Now, the key quantity to study is the Ricci scalar for M4. And the Ricci scalar is the usual way you write it. Now, it turns out that if R4, the Ricci scalar, is greater than 0, we obtain a positive curvature spacetime, and de Sitter is one example. On the other hand, when Ricci scalar is less than 0, then we have anti-de Sitter spacetime. Now, if we take the trace of the Einstein's equation and we ask what happens if we impose R4 greater than 0, we get this interesting equation, d minus 6 and t mu mu, which is the trace of the energy momentum tensor along the space-time direction, should be greater than 4 times the trace of the energy momentum tensor in the internal direction. In string theory, we know d is 10, so the equation becomes a very simple equation. T mu mu should be greater than Tmm. Now, on face value, this is a very simple condition that doesn't look too hard to satisfy. Question is, can we actually satisfy this equation in a two-derivative gravity? So we'll take a few examples and see whether this such simple equation can be satisfied or not. So the string theory that I would be concentrating on is the type 2B string theory. And in this string theory, we'll switch on all kind of energy momentum tensor, and we'll just simply ask this question whether this equation T mu mu greater than TMM can be satisfied or not. Now, let's first switch on L matter, which is made up of fluxes. And this is my Q form fluxes, and this is how I add a flux parameter to L matter. Now, as usual, I have to compute the energy momentum tensor, and I compute the energy momentum tensor. It's very easy to compute. It's just given by this expression, where F square is the complete contraction of F into F. And so this, and Q is the Q form parameter. Now, the condition T mu mu greater than TMM on this will lead us to the following equation: 1 minus Q by 2Q F square should be greater than this quantity. Question is, can this simple equation can ever be satisfied? And I do not want to go into the detail, and you can check for yourself. This equation can only be satisfied if and only if Q is greater than 9. Otherwise, you cannot solve this equation. So this simple equation actually has no solution unless Q is greater than 9. But we know that there are no 10 form in string theory. So which means that no matter how much energy momentum tensor we try to pump in via flux, we can never get a 4-dimensional de Sitter space. So no matter how much energy momentum tensor we put in inside the space, we can never get a positive energy out of the system. It's very surprising that we might think that if we add more and more energy fluxes, we can get positive energy. It turns out that no matter how much fluxes we add, the system never has a positive energy. So that's sad. But all is not lost because we have d-branes, anti-d-branes in string theory. So question is that can we add d-brane, anti-d-brane to give a positive cosmological constant solution? In d-branes, we know that there is the open string of the d-brane combined to give a closed string, which means that all the degrees of freedom on the world volume couples with the bulk degrees of freedom. This helps us to write down the Lagrangian for a d-brane. And the Lagrangian for a d-brane has two pieces. One is the standard, the Born-Infeld piece, and the other is the Chern-Simons piece, where this curly F tilde is a coupling of the gauge field and the pullback of the bulk B field. C is the background monomorph field, and e to the power of F is the standard gauge field topological term over here. And additionally, the tension of the brane is always greater than 0, but this quantity mu p can be positive or negative. That will determine whether we have a brane or an anti-brane. So the brane and an anti-brane typically come from the sign of this term. So now the Chern-Simons piece, which is the piece over here, this particular piece is rather interesting because it actually does not contribute to the energy momentum tensor because it's topological, so it does not contribute to the energy momentum tensor. Which means that the term, the only distinguishing feature between brane and an anti-brane contributing in this system is this part, the second part. The second part, unfortunately, does not contribute to the energy momentum tensor, which means that if a brane cannot give rise to positive energy to the system, then an anti-brane can never give a positive energy to the system. So it turns out that whether so we need to check is whether a d-brane can give rise to a 4-dimensional de Sitter space. So, which means that everything relies on the Born-Infeld piece. And we can work out the energy momentum tensor from the Born-Infeld piece. If we take the trace of the energy momentum tensor of the 3+1 dimension, you get this factor -4 times tension times this factor alpha, which I'll describe soon. On the other hand, if we take the trace in the internal direction, we get a quantity like that. P is the P brane, dP brane. And alpha is given by this quantity, and you can easily see that this is a positive definite quantity over here. And so since Tp is greater than 0, and if we take P equal to 1, 3, 5, and 7, we can easily show that the T mu mu can never be greater than Tmm, which means a D brane or an anti-D brane cannot actually, so which means that neither a brane nor an anti-brane can create enough energy momentum tensor to give us a 4-dimensional de Sitter space. So we cannot use an anti-brane to uplift any space to a positive energy space. So anti-brane can at best break the supersymmetry, but it can never give rise to a positive cosmological constant solution. Which means that if you have an anti-de Sitter space and you put an anti-D brane in this space, it will take us from supersymmetric anti-de Sitter space to a non-supersymmetric anti-de Sitter space, but it will never take an anti-de Sitter space to a de Sitter space. My question is, can P equal to, if you look at here, if P is 9, question is, can P equal to 9 help? It turns out that P equal to 9 means it's a T9 brane, and that actually, because of some global charge cancellation condition, this becomes much more subtle, and that actually does not help. So that's sad. So neither brane nor anti-brane nor fluxes can ever give rise to de Sitter vacua. Now, however, all is not lost because we have Tp less than 0, because you see that from this equation, one could say that if I flip the sign of the tension of the brane, I could actually have T mu mu greater than Tmm. So one might think that it's probably possible that if Tp is less than 0, this could surely help. Now, do such objects exist in string theory? And of course, such objects are called Oriental planes. So there is a chance that Oriental planes can actually help. And what are Oriental planes? I mean, everybody here knows about Oriental planes. So I will just quickly tell you that they look exactly like D branes, where they are non-dynamical perturbatively. Perturbatively, they do not move. Non-perturbatively, they can start moving. Also, they become dynamical object. But they have, interestingly, they have negative tension. And between D branes, the exchange are done by this Klein bottle or Mobius strip. And they are like they are exactly behave like a orbifold point, except that at the fixed point, there is some charge there. And these charge are the Ramon charge they carry. And now if you work it out, the energy momentum tensor as usual comes out exactly with a plus sign, as one might expect. And again, this sign is flipped completely. Alpha is the same alpha we have. So now it appears that we should be able to get what we need. So question is, can we get a de Sitter space from O planes? The answer turns out to be unfortunately not, because for many years it was thought that maybe O planes are actually saving the thing, but it turned out that it's not the case. Because the reason is that because in the presence of O planes, we switch on all other type 2B flux. And therefore we will have to add the contribution of the whole package to see whether we can have a positive curvature solution. So we actually, we cannot simply switch on the O planes like that. We need to switch on the corresponding fluxes, H3, F3, and all these fluxes. And from here, try to compute the curvature. Try to figure out whether this can be made greater than 0. Where G3, F5, and tau are the type to be fluxes, 3 form, 5 form, and axial dilaton. And we also note that this R mu nu, the right-hand side should be independent of the internal coordinate, because this is how we define over here. Anyway, after the dust settles, one can easily check that this quantity, the quantity I wrote over here, actually can never be away from the orientifold fixed point. One can easily show that this quantity is always negative definite. And so that was the result in our 2014 paper, that this thing can never be actually positive definite away from the orientifold plane. So away from the orientifold plane, there is no way we can get a 4-dimensional de Sitter space. The question is, what about at the fixed point, right, where the O plane is there? Or maybe we can use warped compactification. We can change the conclusion. So maybe we can add both, that we go right at the fixed point of the O plane and or use warped compactification. Could we change the result? So we start with warped compactification, and a warped metric is given by the putting some warp factor in this following way. It leads to the following consistency condition. Once we put the warp factor carefully, we get an equation which looks like that. And if you stare at this equation carefully, one can show that this quantity I6 is actually a positive definite integral. Details about this integral is in our 2014 paper, and volume of the internal 6 manifold is greater than 0. So it turns out that if this equation, this R4 can only be greater than 0 if and only if TMM minus T mu mu is less than 0. But we have already seen that this is actually away from the fixed point. This is not possible. If we delocalize the branes, again, it's impossible to have R4 greater than 0, because for branes, we already know that this is greater than 0. So the only way things could change if something drastic happens at the orientifold point. The question is, can this be possible? Well, one way in the literature is to delocalize the O plane, but I never understand what delocalizing a fixed point means, so I don't think I'll be able to make any positive comment on that one. There has been some literature of delocalizing in O planes and trying to figure out whether this could contribute to positive energy. This doesn't look very kosher, so I will not discuss this possibility.
Can I just interrupt? So, Ashok did this work, which you of course know very well, on how the 7 planes of F theory get become dynamical. Is that not what you mean by delocalize? You mean something?
No, they mean that you spread the O plane along some direction.
Well, in that case, the O plane becomes dynamical, then it can move. Okay, it doesn't spread, but it can move. In fact, it turns into some...
No, that's not what I meant. No.
But I think what Keshav is talking about is sometimes called smearing.
Smearing.
Yes. Yeah, I think that might help to the word.
But smearing is allowed for brains somehow, is it?
Yeah, smearing is allowed for some brain, but O plane, it's a little bit controversial topic about smearing and fixed point.
Yeah, but I would think it's a bit artificial to say it's allowed for brains and not for O planes, because we know that O planes are some kind of non-perturbative brains, right? So if brains can be smeared, then why can't?
Yes. So actually, it turns out that smearing actually does not quite help. Actually, it doesn't help, but I don't want to go into detail on that one. We actually found out why it doesn't help there. But maybe I'll answer this question a little bit later as we go to the other effective. We'll probably you'll get the answer out of it. What helps is only the quantum pieces.
Hi Keshav, this is Alok. Sorry, can I just interrupt you for a quick question?
Yes.
Earlier in the talk, you talked about the M6 being either compact or non-compact. Now, why is it that when people talk about the possibility of or the impossibility of getting these set of solutions, they don't worry about the or I don't know. Should one worry about the non-compactness aspect as well? Because one would have to worry about the tadpole cancellation conditions. If you have a non-compact M6, then you're looking at the integral of d star f5 that would not necessarily vanish. So is a tadpole cancellation condition also to be included in addition to this discussion?
Absolutely, absolutely. I'll talk about it. There are a lot of more subtleties will come in. And if you take a non-compact internal space, the Newton constant, 4-dimensional Newton constant becomes 0 exactly. Because it's inversely proportional to the volume of the internal space.
Right, right.
So we don't want to take a non-compact. We need a compact internal space, which leads to all kind of questions like what about anomaly cancellation, charge cancellation, what about Bianchi identity, everything.
Right, right.
Yes, all of these will come into, and that's what, as I'll talk.
Okay, great, thanks.
Yeah, I'll talk about all these things as we come along, as we go along.
Okay, thanks.
So, well, it turns out that the delocalization is a little bit tricky and actually does not help. So to analyze this situation right at the fixed point, we will go to a more elaborate theory, which is M theory. In this theory, we should be able to understand what happens exactly at the fixed point. So what is M theory? M theory has been variously known as, everybody knows about it. I don't know why I put that slide, but M is magic, mystery, or matrix. And as we know, the law is one ring to rule them all. M theory can define all these theory. But the reason of going to M theory is, one good thing about going to M theory is that it can repackage all the fluxes into one nice package form. The 3 form, axion, dilaton, 5 form, all become packaged inside that. Another important thing is that M theory, the action can be written down, at least the supergravity. In type 2b, there is subtlety about how to write the type 2b action, so that also is an issue over there. But M theory, everything is a little bit cleaner. And also everything comes in a nice packaged form, so it's easy to control that theory. Also, in addition to that, orientifold planes of type 2b theory can become smooth spaces in M theory, which is what we can actually exploit. Now, once we take this O plane, fluxes, and brane in M theory, we'll end up in the following consistency condition. So the first term you see that it's integral over all the fluxes over here. So this is where all the fluxes comes in. The last term is exactly the brane and an anti-brane. These are the 3 brane and anti-3 brane in M theory become M2 and anti-M2 brane over here. And this is the contribution, this whole integral contribution comes from the O planes. Now the consistency condition, which basically come from one condition that Alok just talked about. It also comes from the smoothness of the warp factor or some level anomaly cancellation and all. But the condition is the following thing, that this whole integral has to vanish. This is the condition we get from M theory.
Sorry, Keshav, can I really apologize. I just had one confusion. Can I please get that clarified?
Yes, yeah.
So I'm assuming you are dealing with a class of warp compactifications now, right?
Yes, yes.
Which means that there is a non-compact radial coordinate.
In 3+1D.
No, in the transverse in the M6.
No, there is no non-compact internal. There is no non-compact.
So what does the warp factor depend on?
It depends upon the internal coordinate. But
I see.
Yeah, it's not non-compact. So I should clarify this.
Okay, so your M theory 4-form fluxes are going to satisfy the Witten's quantization condition of fluxes.
Absolutely.
Okay, all right, thank you.
Yes.
I'll shut up now. Yes, thanks.
No, please ask. Please ask. Please ask.
Thank you.
It's going to be more subtle. It's going to be much more subtle. as you will soon see.
Okay, thanks.
So right now, all the fluxes are here. These have no time dependence. Of course, these are time independent fluxes. And this is the consistency condition, and lambda is the cosmological constant. Now, if you stare at this equation, you'll find that everything is positive definite. G square is positive definite. H square is positive definite. Number of brane and an anti-brane is positive definite, equal to 0. There is no way we can make the cosmological constant positive definite in this equation. The only way we can easily make lambda less than 0, and that's the reason why lambda less than 0 are so easy to get in string theory. Lambda equal to 0 is also possible if you switch off the fluxes and have no brane and an anti-brane. Lambda equal to 0 is possible. Lambda less than 0 is possible. Lambda greater than 0, there is no solution for this system, as you can see. And that is the problem comes in, no matter how many flux you add, or brane, or an anti-brane, or O-plane, or anything you add, this is the consistency condition will land up in a bigger theory, which is M theory. And that bigger theory has no solution with lambda greater than 0. So no brane, no anti-brane, no fluxes, no O-plane, nothing can ever give rise to a positive cosmological constant solution in the theory. Now, only way this equation can change if there is an additional piece in this equation. And what is that? So that's exactly what I said. So this is my conclusion, that if a theory has only 2 derivative gravity, if the theory has only 2 derivative gravity, no other higher order term in the theory, that theory will never have a de Sitter solution. In other words, Einstein theory, 10-dimensional Einstein theory, will not have a de Sitter solution, period. There is no solution at all possible in that theory. Now, question is, can we change this conclusion? And the answer is, of course, that as Hawking said, that the only way we can change the condition is if you introduce quantum correction. So question is, how do we implement the quantum corrections in this? To implement the quantum correction, we'll first assume there is a possibility of existence. And then we'll ask what would go wrong. What would go wrong in such an analysis? So again, for simplicity, we'll analyze the problem from M theory, where the number of fields are limited and the equation of motion are easier to handle. And in this discussion, I also show that even the quantum terms are very subtle. Even just by throwing in quantum terms, we actually will not be able to get de Sitter. And that is the root cause of swampland. That swampland idea of Wafa is a very subtle and a deep idea as far as my understanding goes. And is a very difficult way to get out of that conclusion. So let's deal with adding quantum terms and see whether we can change the conclusion or not. So how do we proceed? We will ask the following question, that let's put everything together in M theory in 2B, and then we'll lift it up in M theory and ask whether a solution like this, which I showed in the screen, is it possible or not. So if you look at this equation, this is exactly lambda is the cosmological constant, y is the coordinate of the internal space, this internal compact internal space, HR is the warp factor, and R is the one of the coordinate, which is, we call it R radial coordinate, but it's actually compact coordinate. We'll make one assumption that the dilaton remains a constant, but of course this could also vary. The only reason we take dilaton constant, that we found that there is a consistent solution with that. And one good thing is there's a string metric and Einstein metric coincide, so we don't have to worry about going to string frame or Einstein frame. So the question is, can a solution like this, when lifted to M theory, or can a solution like this in type 2B, can such a solution exist in string theory? One more thing.
So Keshav, just to clarify, so now you are in the regime of the work you have done, correct?
Yes, now in the regime of the work I have done.
Okay, thanks.
Yeah. So previously also was, so Maldacena and Nunes had shown brain and an anti-brain cannot get. Gibbons had shown fluxes cannot give. Maldacena and Nunes had shown brain and an anti-brain cannot give. What we showed in 2014 is that even the O plane actually is tricky because we analyzed everything from M theory. And we found that previous equation I showed one was the equation in 2014, where we showed that there is a consistency condition that has no solution, even in the presence of O planes and all.
Thank you.
So now we elaborate.
Sorry, can I just interrupt? I'm a little confused. Yes. What happened? Maybe I was distracted for last minute or so. This is the time-dependent space-time?
Yes.
And you said something like, we'll assume that quantum corrections can give us some solution. Where did it become necessary to say that has to be time dependent?
Right now, right now here the conclusion here was that there is no solution in two derivative gravity.
Or even with quantum corrections?
Even the two derivative gravity anyway, there will be no.
No, that's fine. After this, you had this Hawking's quote and all that. After that, what was the observation? You said
so the observation is that, so then people ask the question that, okay, maybe the quantum correction can save the day.
Yes.
So the question is, okay, these are words, of course. So can we actually analyze the quantum correction and see whether can quantum correction can actually save the day, or there is no solution possible at all? Maybe string theory doesn't have a decision.
Right, all right, but then I'm just wondering, from here, quantum correction to time dependent seems to be a bit of a leap, no? Yes.
Okay, so so here I make, so I should apologize for not clearly saying that. So here, question is, how do I analyze the quantum correction? So there is one way of analyzing is to put an ansatz and ask whether this ansatz is a solution to the equation of motion in the presence of quantum correction. Okay, is that okay? So now question is, what kind of ansatz I will take, and the answer that I want to take is a metric ansatz of this particular form. Okay, and you see this is exactly a de Sitter space, 4-dimensional de Sitter space in the flat slicing. So this is exactly the
okay. So the usual 4-dimensional. You haven't added something extra to the space-time. It's just usual 4D de Sitter in some special coordinates in the flat size.
So this is so question is this a solution of string theory? Is the question. So now clearly we showed that without quantum correction it is not a solution, and so can I add quantum correction and show that this is a solution or not? Now this turned out to be a much more tricky analysis, and this is what we did in 2018 and then a bit later on also. Now again, this analysis in 2B is a little bit harder to do, so we just lift it to M theory. It's just for bookkeeping. It's easier to handle this thing in type 2B side. So I lift this guy to 2B, and now if I say that this is a solution to string theory, if it is, then also I need to switch on some fluxes and other thing to support it. So since I don't know how much fluxes I need to switch on, what I need to switch on to support all of these things, I'll assume that in M theory, I switch on a fluxes. If M and PQ are the internal coordinate, I'll switch on some fluxes. Let's first assume that I switch on a time independent fluxes G, M, and PQ in the internal space, and it could be anything arbitrary. And the claim is that this kind of fluxes can actually support a background like this.
Sorry, Keshav, is it correct in assuming that everything that you've discussed up to this point, I mean, before the slide, all the conclusions, all the no-go theorems were implicitly or explicitly assuming time-independent backgrounds only?
See, when we say de Sitter space typically is always a time-dependent background.
Yeah, but the internal space.
Internal space is time-independent, yes. Yes.
Or is that going to continue, or up to now it is in time-independent?
We don't know what is going to happen with GM.
So you're allowing it to be time-dependent. I think that's what Alok was asking.
Right, right, exactly.
It will turn out to be that this also has to become time-dependent.
Okay. Exactly.
But if
and the particular choice of 1 over mod t squared, is that motivated by something, or is for dimensional reasons, or?
This is actually, so I also didn't know, but it turns out that it's something the cosmologists know as a flat slicing of de Sitter space.
But it's not very surprising, right? Because ADS also has a similar thing with some.
Yeah, so the 1 by t square is like the 1 by z square, right? Of ADS.
Yeah.
Exactly.
Oh, okay.
Exactly.
And the last dumb question is, why do you guys have to start with 2B? Why not M theory right away?
Because we wanted to show it in 2B. Yeah, that's a good.
I mean, yeah, if it worked in M, you kind of assume that.
Could have done also in M
something
theory,
like
but 2B is because KKLT was also in 2B, so everything was addressed from a focal point of KKLT basically.
Okay, all right.
Hi Keshav, this is Shahin. So let me also add a comment here.
Yes.
Do we know what are the so-called alpha prime type corrections in M theory? So in type 2B, we know them. We can compute them through string theory. How do we know about these higher derivative corrections in M theory?
We will take all possible corrections, all generic, all possible correction, all powers of curvature, all powers of G flux, all non-perturbative term, all non-local term, everything.
Okay.
Keshav, can I put in my 2 cents worth on that question? Yes. So basically, this is this old work in '97 by Michael Green, Van Hove, and Michael Gutterle, which actually addressed this the question was just asked. And there are 2 routes to getting the answer. One is through a 4 graviton scattering amplitude and working out the contribution in defective theory from that amplitude. And the other is through pure supersymmetry. So either way, you end up that the analog of the alpha prime correction, which would be the corrections for the higher powers of Planckian length, would be quarting in the curvature tensor. And there are 3 varieties of them. So that's known, up to quartic in R.
But we'll go beyond that. I'll not have time to say all of these things in the talk, of course. But in our paper, we took all possible combination of curvature tensor to the power of any power, all possible combination of G flux to any power. So that's the way we actually did. So maybe I'll just shine that thing. If I get 5 extra minutes, I'll just show something over here, so that since I'll not have time to actually talk about all of these, I just wanted to flash something like that. If we take, so we will take all possible combination like that, all derivatives, can you see the screen?
Keshav, no, something is wrong.
Oh no. Oh, okay, let's see.
It seems, yeah, it's warped over our space-time.
Yeah, there's certainly a warping.
Okay, so let me see how I can repair this. Okay.
So I think in the share option, you will get different things to share. You have to choose the right thing that you want to share.
Seems to be back.
Okay. Let me just try to share.
So Keshav, you don't need to minimize that presentation. You just go to your share option and look for options, things that you want to share.
Oh, I see.
Minimize it. Yeah, you don't need to minimize that.
New share. Okay. Okay, here. Share. Clearly, I am an expert in the Zoom thing. I have no idea how this works. But can you see now?
Yes.
Yes.
Okay. So this is the kind of term I take. All possible combination of R, M, and PQ. These are various core I, M, and PQ, AB, and all these. So all possible combination we take like that. All possible combination of curvature, all possible combination of G fluxes, all possible combination of derivative. So quantum terms will be typically, and sum over all LIs, and sum over all MI, NI, and so on. So this is the kind of term. Since we don't know exactly what kind of term would come in the theory, we'll take everything allowed. all possible combination of quantum terms. So these are only the perturbative series. Similarly, there will be a non-perturbative series like that, which is exponential of the quantum terms on the brain, or on the M5 brain instanton, or M2 brain instanton and all. And then we'll take, which are non-local terms also, which is 1 over the derivative. Here you see that there are derivatives, but there could be term inverse the derivatives. We'll also take. So we'll take non-perturbative, perturbative, non-local kind of term.
And Keshav, is it correct that you guys don't worry about any constraints on L's because you're dealing with a non-supersymmetric de Sitter? You want a non-supersymmetric de Sitter solution, right? So you don't worry about any constraints on what kinds of R's and what kind of indicial contractions are permissible.
Correct.
Okay. All right. Thanks.
Yeah, because non-supersymmetric, that's one advantage we get. So it's since we don't know all of these things, we'll take whatever available.
So
you might ask,
question. Sorry.
You might ask why not? So we took e to the power of something. What about e to the power of e to the power of something? There could be. So we try to analyze this series.
Keshav, can you hear me?
Yes.
Sorry. So is there some? So if you take all these terms, does it mean that you're somehow assuming some form of something like a resurgent trans series or something like that? What is the
exactly? The so when we take the non-perturbative sum, we made a Borel sum of the series to put it in the exponential form.
So the assumption is basically that the effective action has that form. Is that the assumption that implicitly you're making?
Yes. Okay. Or then more tricky question can come, because this is an effective action. You might ask, how come in a time-dependent background there is a Wilsonian effective action?
Right. Yeah. No. Yeah. I mean, assuming that all these. Yeah. But I'm just saying the context.
So, again, I'll not have time to say all of this.
Thanks.
But I'll just tell you what I prepared a little bit, not too much, but. Anyway, so I'll quickly go through, I'll just point out why WAFA's analysis is subtle and non-trivial, not from the point of view but if you go deep inside the theory, we see that there is an issue, very deep issue with the de Sitter. Anyway, if you switch on fluxes like that, GM and PQ, first let's assume they are time independent. It turns out that to solve equation of motion, you also need some fluxes which should have some legs along the space-time direction. So M is the internal direction, MP, and it has some specific form in this particular way. So these details are important, but can be easily figured out by looking at the equation of motion. Now, we require the quantum series in M theory, and I'll just flash out one particular non-topological piece over here. And of course, there are also topological pieces, so perturbative, non-perturbative, non-local, but then there is this whole series of topological interactions also. M theory has weird stuff. So this is how, like any arbitrary derivative, any arbitrary power of curvature, any arbitrary power of G fluxes, plus ... and each of them are suppressed by some powers of M Planck. This is the kind of potential we can see in M theory. Now, what are the quantum correction needed for us? So it turns out that the quantum correction, the energy momentum tensor from the quantum piece, basically, by the way, how much time I have?
Yeah, you can take easily 15 minutes more.
15 minutes, okay, fine.
Yes.
That should probably do. So the energy momentum tensor from the quantum series turns out to can be written in the following way. It's a linear combination of specific things like that, where you note something. I have divided the quantum energy momentum tensor as a series in which I have extracted the time part, which is lambda t squared to the power of any arbitrary. And then there is a CMN, and the sum over all i's are there. And CMN is basically a time independent quantum contribution. So that I can divide this series in this particular way. So this is what we wrote in 2018 paper, and in 2019 with Mir and Maxim and all, we actually could show that this indeed can be made in M theory. Even the perturbative, non-perturbative, all of these things can actually be divided into a piece which has a time dependence exactly like that with a time independent piece. Now, this guy contains all over what I was talking about, the whole series of perturbative term, whatever you can think of. all the non-local term, all the non-perturbative terms and everything. By non-local, I mean inverse derivatives and all. The non-perturbative term, which is e to the power of something. All of these things are inside that. Now, just writing this is not enough. So question is, can we actually quantify this CMN? And it turns out that the answer turns out to be yes, that we can actually quantify the CMN. And remember, the CMN, which we wrote over here, should not depend upon time, and the time part is extracted out. So question is, are there combinations like that in M theory? And it turns out that a combination like that is there. Although the time appears over here, you can show that actually when you take the inverse of when you raise and lower the power of the G fluxes, they have the inverse metric that contains the time, and that time actually cancels this. So this whole quantity actually is completely time independent object. Assuming the G flux themselves are time independent, the curvature of course becomes time dependent, or time depending on what kind of curvature we are taking. If it is along the space-time direction, they take time dependent pieces. But another thing you may note that every such term is suppressed by powers of M Planck, which is important because in such a theory can be defined with respect to G string hierarchy or the M Planck hierarchy. So you can see that all of these terms are actually, so there is a whole series over here, there's a whole series over here, suppressed by some kind of powers like that. And that is exactly what I was saying. This whole quantity is a time neutral. So you can divide these quantum pieces as a time part has come out over here, and time dependent piece, time independent pieces like that. Note also that it's this K, this quantity A gamma can take any value, any integer value. So which means that there are in fact actually an infinite number of such terms for any given value of K. Yeah. Now, other bad thing or interesting thing happens in the type 2a side. If I go to M theory, the string coupling in the type 2b side is time independent, but in the type 2a side, the string coupling itself becomes time dependent quantity. Now that's interesting because we are dealing with a time dependent background. And right now, let's assume that the internal space itself is time independent, just to simplify the matter, but this will turn out not to be the case.
Keshav, can I ask something very simple?
Yes.
So you were saying that you need the whole series of non-perturbative corrections to get a de Sitter or not? I mean, this is
everything.
You need the whole, but why exactly you need the all orders of non-perturbative corrections?
You will see. Maybe I'll try to explain that. Let me explain this, and then we will see. Here I will tell you what is the problem. Okay, what is the problem with quantum correction and all this thing? I'll kind of motivate the swampland kind of argument that Pafa has given in a different way. From there, how do we extract the de Sitter solution out of this? It's so let me come to this, and then maybe you can ask me a little bit later.
Yeah, sure.
Sure. Okay, but at least you notice that since the de Sitter is a highly quantum system, it's not a classical system. So, and we saw any amount of classical thing does not help. So we take all kind of quantum correction. And question is, do all quantum correction contribute or not? Or maybe all quantum correction actually, even if they contribute, they do not give rise to a consistent solution. So let's see. So our first assumption is all the fluxes that we took is time independent. And all the GM and PQ fluxes that we took is time, which means in the type 2b side, the H3 and F3 fluxes are time independent in particular. And the internal space right now we are taking time independent. So the answer is that the space time has time dependent part, which is the 1 over lambda t square, and the internal space is no time dependent. Can this solution be can this solution be realized in string theory? Now, if you do that, if you lift this guy to M theory, then the string couplings become lambda t square, which is time dependent quantity. And therefore I can trade this lambda t square, simply write it as GS, which we'll call the G string. And we see that the quantum series can be written as G string times a series which is suppressed by powers of M Planck. In other words, the quantum energy momentum tensor will divide into G string to the power of something suppressed by various powers of M Planck plus G string to the power of something suppressed by various powers of. Inside everything is time independent, in other words, G string independent, but they are suppressed by M Planck. So you see this system has an M Planck hierarchy because there is 1 by M Planck and so on. And then there is a G string hierarchy. If alpha 1, alpha 2 are, if alpha 2 is bigger than alpha 1, then we know that when G string is smaller than 1, we can ignore this guy over here. So this looks like a reasonable quantum term in which there is a M Planck hierarchy and there is a G string hierarchy. Is that clear?
Keshav, are you implicitly assuming that lambda, the cosmological constant times M Planck squared, is much bigger than 1? I mean, you're looking for some
smaller than
classical.
Smaller than 1.
Yes, smaller. So basically, that's a classical de Sitter, not Planckian.
No, not Planckian de Sitter, definitely not.
Okay.
And people who are expert on this one would also note that when you take lambda, G string is smaller than 1, this will put a constraint on the time itself. You see that? T should be smaller than 1 over square root of lambda. And that exactly, as you can see, if I take quantity this G string smaller than 1, you see that T becomes smaller than 1 over lambda, square root of lambda. And that turns out to be a new recent result by Diwali, who found that T smaller than 1 over lambda is some so-called the quantum break time. But I don't want to come to that particular issue, but I'm taking G string to be smaller than 1 to control the series over here. But you see, energy momentum tensor, despite, even if we don't have any knowledge, we can at least write it in this formal way, in this particular way. But this series is good because it has a 1 over M Planck suppression, and it has a G string outside. So there's a G string hierarchy and M Planck hierarchy. Now, it turns out that this is unfortunate because this was all the perturbative series I took over here. But if you actually carefully take all the perturbative and non-perturbative series, this quantity beta actually can pick up positive and negative value.
Sorry, Keshav, I apologize. Is there some tension between the fact that you have a string coupling which is time dependent and the assumption that the dilaton of the type 2b was a constant?
If you T-dualize this whole quantity, it's become time dependent. Dilaton in type 2b is time independent, but if you T-dualize the 2b configuration to 2a in a time dependent background, the type 2a dilaton becomes time dependent.
Oh, okay. Oh, this is type 2a.
Yeah, because we are going to M theory now.
Oh, yeah. Okay. All right.
So this is all in M theory. So G string becomes, which means in the M theory language, the 11 dimensional radius become time dependent quantity.
Okay. All right. Thanks.
Unfortunately, to deal with this kind of background, because this is the kind of background we want to study for de Sitter to exist. So there's a kind of at least kind of hierarchy we see over here. Now, the unfortunate thing is that if we actually add the non-perturbative and all other things, this beta can take positive and negative value both. But that's not good, because in a given bracket, you can have both positive and negative M Planck. That means this in a given bracket over here, if you have both positive and negative M Planck, then we have lost the M Planck hierarchy in this thing. We cannot say that I take M Planck going to infinity and I can cut off the series. If I take M Planck going to infinity, if I have a 1 over M Planck suppression, I can easily cut off the series at some point. But if there are positive power of M Planck, I cannot cut off the series. So you see, if there's a positive and negative power of M Planck in the series is highly unfortunate, because neither M Planck going to 0 or M Planck going to infinity, in either case, you cannot cut off. So you cannot terminate the series at any value of M Planck. If you take M-Planck going to infinity, you can terminate 1 over M-Planck values, but all positive powers of M-Planck will start contributing. On the other hand, if you take M-Planck small, then all 1 over M-Planck will start contributing. So if this series have M-Planck positive and negative, then this series will lose its M-Planck hierarchy. And it turns out that if you add non-perturbative correction to in M theory, we can easily show that there are no longer M-Planck hierarchy in such a thing. So that means the only saving grace for such a series is that maybe there is a G-string hierarchy. This way I can at least control some part of the series if G-string is smaller than 1. On the other hand, if you lose the G-string hierarchy and all hopes are lost. So question is, does the G-string hierarchy survive in our final quantum expression? Well, you may ask, why shouldn't it? Because it appears in the definition of the energy momentum tensor. But wait, if you actually work out the equation of motion, and you actually work out the Einstein's equation of motion in the internal space, you will find that there is no more G-string suppression in this equation. Where alpha k turns out to be literally an infinite number of all alpha k, which give rise to G-string to the power of 0. So this equation scales as G-string to the power of 0. This side scales as G-string to the power of 0. So in the quantum piece, as somebody was just asking, do we need to take all the quantum piece? Well, we don't need to take all the quantum piece. If you want to compare the Einstein equation, you just look at the first term of the Einstein equation, Einstein tensor, and that scales as G-string to the power of 0. You can easily check the scaling. The flux piece surprisingly also scale as G-string to the power of 0, which means that the quantum piece in this particular series, in this given series, we just ask, what is the G-string to the power of 0 from here? So what are the value of alpha 1, alpha 2, which can give rise to G-string to the power of 0? And we start searching what are the value of alpha 1, alpha 2, which alphas are 0. And sadly, there is an infinite number of such pieces over here, which have G-string to the power of 0. Which means that this equation has no solution. So we have lost both the G-string hierarchy and the M-Planck hierarchy, which means that time-independent G fluxes and time-independent internal space will not have a simple 4-dimensional effective field theory description because there is no more G-string hierarchy. But you may think, okay, we lost the G-string hierarchy for the internal equation of motion. What about the space-time equation of motion? Maybe there is some kind of hierarchy there. And if you actually work out the space-time equation of motion, it turns out that we need to look for alpha k equal to -2. And we look for G-string to the power of -2 pieces. And we find that there are again an infinite number of G-string to the power of -2 contribution. So literally there is this C mu mu k has no M-Planck hierarchy, no G-string hierarchy. So you have an equation which left-hand side is given by that, right-hand side is given, but the right-hand side has no, you cannot terminate this series. There is no Borel sum you can do or anything like that by which you can terminate this series. So T2 is the number tension of the brain. And this is the difficulty of the swampland. This is what exactly Waffa was, I think, is trying to say in his paper, that there is no de Sitter solution in string theory. What our conclusion in 2018 paper was that if you take time-independent G flux, if you take the time-independent internal space, this system, no matter how much quantum correction you pour in, it put infinite number of quantum, perturbative, non-perturbative, non-local, everything you pour in, there is no solution to this system. The system has absolutely no solution. There is no de Sitter solution in a theory like that. The metric that I showed in the beginning with 1 over lambda t square into the space-time part plus an internal part which is time independent does not exist. That solution does not exist in string theory. In other words, this is what I meant, that all the G-string pieces go away. This guy has positive and negative power of M-Planck. And you see this series is infinite, this series is infinite. There's no way you can control this series anymore.
Sorry, Keshav. Not being able to control doesn't mean that it doesn't exist.
Correct. You may say that maybe none of these terms cannot exist. But since we don't know exactly what are the powers also, this C11, C12, C21 are these powers of curvature and all this thing which I
I think what Swampland is saying is that it doesn't exist, just period. But you're saying it's not possible to control it. They're, I think, different, right?
This is what we are getting. It is not possible to control it, but I will not end this talk with a negative note. I'll end with a positive note. Okay. But at least with what our conclusion was that since original Bafa's analysis was delta V by V greater than or equal to C, there was no. This looked like an ad hoc way of putting it, and you cannot simply say that delta V, I want a theory with delta V by V greater than or equal to something, greater than or equal to quantity C. We didn't want to go along that path. We wanted to ask from deep inside the theory, what would go wrong with an ansatz like that? With an ansatz with 1 over lambda t square into the 4th dimensional space-time plus a time-independent internal space and time-independent G fluxes, what would go wrong? What we found is that we found a serious problem of having a series, ending up a series. At least we saw that there was, in such a series, there was no G-string or an M-Planck hierarchy.
So
maybe it still has a solution. Maybe the system still has a solution, but this is what we found.
So Keshav, I had one quick question.
Yes. Yes.
So, so how does KKLT fit into this? Is it so? That's not. It's somehow. It's not in parametrically. It's not. It's not in parametric. Parametrically controlled regimes in some sense. So, how does that fit in with your statement here?
I'm actually working on a paper. We're trying to clarify. So what KKLT did is that if KKLT, can you give me a little more moment? I will answer your question. Ask me towards the end this question.
Sure. Yeah.
Ask me the same question towards the end. Maybe I'll try to answer.
So Keshav, I have a question on this particular expression. Yes. So each term in this square brackets themselves are infinite, and you said that I think including non-perturbative corrections, they can be, you can give meaning to each term inside the square bracket, but then you have infinite number of such square brackets, which you cannot understand. Was this your statement?
Yes, but also inside this bracket, you see that beta can be positive or negative.
Yeah, I understand that. But then you said that inside this bracket, you could include non-perturbative corrections, and somehow you could give meaning to each term inside the bracket. Yes. But when you have to add all the brackets, you do not know how to add them up.
That's right. That's right.
Okay, thank you. Okay.
Yes. Any other question? So this is our way of approaching.
Sorry, Keshav, just quick clarification. You said that you can go to a subsector. Say, for example, in the previous slide, you had G string to the power -2 for the space-time.
Yes.
And in that subsector also, you cannot further classify the different powers of M string. M Planck.
I can give you a very simple reason which we got in our paper with Mead and Maxim and all. It turns out that every such quantum term I showed you, this whole infinite class of curvature, they scale in a very nice way with respect to this quantity G string. Okay. And if you take a time-independent flux, we can show that it goes as G string to the power of, if you take time-independent flux, it goes as G string to the power of, say, A minus B. Okay, that quantity goes, where A is related to these powers of Li and B is related to some powers of Li. Okay. So it goes as G string to the power of some quantity minus another quantity, where this quantity is a function of Li. Is that okay?
Mm-hmm.
Okay.
Yeah.
Now, if I give you a quantity A minus B and I ask you if I want G string to the power of 0, if I say A minus B equal to 0 and A and B are integer, there are infinite number of solutions to that system. It's exactly what happens.
Mm-hmm. Another quick question. Is it because of the way this series was written in the first place as an ansatz? Could this be reorganized, for example, into there's some e to the power 1 by G string squared, which as a perturbative series?
Indeed, there is a separate way. There is another separate series which can be reorganized by Borel summing the whole thing to e to the power minus 1 over g, e to the power minus 1 over g string square. Unfortunately, that series also has similar problem.
I see. Thanks.
Yeah. So that is my more recent paper this couple of months ago. Okay, so this is the problem we see. So there appears to be no simple 4-dimensional effectivity description of the system. Now, if you ask, you may say that, okay, quantum pieces were creating so much problem. What if I switch off the quantum pieces? Well, of course, if you switch off the quantum pieces, it turns out there is no solution, because remember, if I did not have any quantum pieces, then this was the case, this was equal to 0. This first line was equal to 0. If I add the quantum pieces, these are these quantities CAA, CMM, and C mu mu. You see, when I add the quantum pieces, it contributes to that previous equation I wrote by adding this particular thing. So if you want lambda greater than 0, then the only possible way lambda greater than 0, because this is positive definite, the first term is positive definite, the third term is positive definite, and the middle term is also positive definite. The only way to get lambda greater than 0 solution, if this quantum series, you see, if it sums up to a negative definite quantity. So I need that all the quantum series should sum up to a negative definite quantity. But unfortunately, it turns out that since CAA, we just showed that you cannot control that series. CMM you cannot control. C mu mu you cannot control. So you now have an interesting situation in which sum of all the quantum series which you cannot control is smaller than 0. So this whole system cannot be controlled anymore. So that is the problem with if you take the time independent quantities like that. So, when we wrote our 2014 paper, we actually had this relationship. We had this relation. At the time, we didn't know how this CAA, CMM, and C mu mu look like. In 2018 paper, when we analyzed this, we found that these are actually with time independent fluxes and time independent internal space, you cannot actually control the whole thing. So around the same time, around 2018, actually, Wafa's paper also came up. And then we could compare our result with the paper of Wafa. And from our understanding is that even if you do not want to argue delta V by V case, you can actually go deep inside the theory and ask whether you can have a controlled hierarchy in that thing. And we find that we do not have an hierarchy. So our conclusion in 2018 was that de Sitter space was very negative, because we thought de Sitter space does not exist at all in string theory. Question is, and then in 2019, we actually, can I get 5 more minutes?
Yeah, sure.
I apologize for taking time, but I should be done in a few pages actually.
Sure.
Yeah, so then in 2020, actually, I started working with Shuddho, postdoc here, and again with Radu. And we asked the question that maybe taking de Sitter as a vacuum is not the right way to do in string theory. Maybe de Sitter actually is not a vacuum. Maybe it's a state in a theory. And we wrote up this paper. And after we wrote this paper, actually Diwali from somewhere contacted us. And he scolded us saying that this was my idea. It was actually Diwali many, many years ago, 2017, he had an idea that de Sitter is actually a state. And we didn't know about this. We were addressing this problem in a different way. And Diwali originally thought about it, wrote a very interesting paper saying that de Sitter is actually, well, he was dealing with 4-dimensional de Sitter, not string theory. So we asked the question, okay, the whole idea of viewing it as a vacuum is actually, will never work, I think. So maybe it's a state in a theory. So here is Shuddho and here is Radu. And so I'll just summarize because I don't have much time. So maybe it was all not quite correct to consider it as a vacuum. Maybe it's a state. But it turns out that it's still a hard problem. So question is how to realize this as a state. Again, I will take this, I'll take this same ansatz, 4-dimensional thing, and I'll ask how can we embed this in string theory? And one of the answers we initially took was exactly that. And this actually did not quite work. And what actually works turns out to be an internal space that also has a time dependence. You can see that there is a time dependence of the internal space also. Not only that, the fluxes will also have to become time dependent. So now we are in an even more tricky question. The internal space become time dependent, the fluxes become time dependent, but we also wanted to keep the Newton constant time independent. So this leads to a very strong condition on the, we divided the space into 4 plus 2 in type 2b. That F1, F2 square has to be 1 to keep the Newton constant time independent. With this, we ask the question, can this metric configuration, which is given by equation 1, can it be realized as a state in the theory? And the only state which behaves almost like a classical thing is Glauber-Sudarshan state, or the coherent state. So our claim was that de Sitter space is actually a coherent state in string theory. Now, two questions will arise. Why do you want to realize it a coherent state, and how can we realize it as a coherent state? Now, let me answer the first thing. The only way you can define it as a coherent state, you take time-dependent degrees of freedom. So everything has to become time dependent. All the fluxes have to become time dependent. We'll only keep the dilaton time independent just to control it. But all the 3-form, 5-form fluxes, everything become time dependent. So in M theory, even type 2A G string already is time dependent. All the G fluxes become time dependent. All the internal space become time dependent. Everything becomes time dependent. But we immediately land up in a big problem, because in our study of quantum mechanics, a coherent state is by taking a vacuum, harmonic oscillator vacuum, and just pushing it up and leave it and it will oscillate. This is how the Glauber-Sudarshan state was created. But the problem was that in string theory or in M theory, there is no free vacuum. There is only interacting vacuum. So we have to construct the Glauber-Sudarshan state using this interacting vacuum. So this was a technical problem, but we eventually found a way to construct such a state in a theory. But once we constructed such a state, it actually started giving us interesting answer. For example, it started telling us why Wilsonian method can be trusted. Because Wilsonian method, for example, if you want to define a Wilsonian method, we have to go back to our vacuum still remains supersymmetric and the state breaks the supersymmetry, that is de Sitter state. So we wanted to see whether we can answer this question, and I will not go into the detail about this thing. I'll just flash the last bit of thing, that why is still a very hard question. It turns out the reason why this is a hard thing is because we have to show that the system is quantum mechanically stable, of course. But the more difficult question is that in a compact internal space, the fluxes has to be quantized. How can we have a quantized fluxes when the internal space and the fluxes themselves are time dependent? So this we had to answer, of course. Now, we also know how the anomaly cancellation has to work. In other words, how Gauss law is defined in an internal space. Again, how the moduli stabilization can be understood when the moduli themselves are varying with respect to time. How the no-go conditions are satisfied now. How the strong weak energy conditions are satisfied. How can we understand the perturbative correction? How can we understand non-perturbative correction? How can we understand non-local term? How do we keep the 4-dimensional Newton constant time independent? How positive cosmological constant can be generated? How does the 0-point energy get renormalized in such a non-supersymmetric background? How does the geometry topology of the compact space can be understood, which is now not a Calabi-Yau space anymore? How Bianchi identity are satisfied? How the Swampland criteria are averted? how the early time physics should be understood, how the inflationary paradigm may be recovered from our analysis, how the other solution can be found, all should be understood in a top-down method. And the problem is that you cannot simply say that I will answer a few questions and leave it for later. You need to answer all of these questions to actually get a consistent solution. And in our paper, we try to answer many of these questions, which I would request you to have a look at it. So this is all combined together makes it a very, very hard problem. And that is the reason why finding de Sitter space in string theory is not an easy problem at all. It's, in my opinion, a very, very hard problem. If you go deep inside the theory, you'll start seeing all these deep problems from hierarchy and all this thing. So I'm sorry for taking at least 10 minutes more than that. So this is the summary. I mean, of course, we showed that in 2-derivative gravity, it's impossible to get a 4-dimensional solution. The conclusion doesn't seem to change once quantum corrections are included. These quantum correction appear from all these stuff over here. So our conclusion is that it appears that the only way to save the situation here is to view de Sitter space as a coherent state and not as a vacuum. And in my opinion, maybe I'm wrong, maybe these series can be controlled in some clever way. But right now, my understanding is that there is no de Sitter vacua in string theory. There is a state in the theory, which is a de Sitter state. Supersymmetry is broken spontaneously. Well, hopefully I was able to convey the main point of our work. We are trying to work out the implication of this one. Merci beaucoup.
Thanks, Keshav, for this very nice talk. And you can also, if you wish to, you can actually continue this in the conference when you're speaking. There.
Yes, I will talk about the other aspect of this part in the conference.
Okay, so let's take more questions.
Somebody was asking about the KKLT thing.
Yeah, I mean, I have many questions. I mean, it was a very interesting talk. But yeah, I think I'll just ask the KKLT question and be done with it. Yes. Maybe we'll talk.
So here is my understanding of the situation. Maybe I'm not. If you view the KKLT as a time-dependent 4-dimensional space with a time-independent internal space with H3 and F3 fluxes time-independent, then I don't think this is a consistent solution in my understanding.
I see.
The situation. It's inconsistent with respect to TCC, it's inconsistent with respect to swampland criteria. On the other hand, KKLT never makes any comment about what kind of, they don't specify exactly what kind of fluxes and all they take.
And so, I was asking that from the point of view of your series, so how does that fit in was what I was trying to understand, in the sense yes. that, you know, like somehow KKLT is definitely not expected to be in, you know, some asymptotic region. So where do you see that in the context of your series is my question.
Yes, so so KKLT has this dw square minus 3w square. So that comes from the flux square piece, h3 square plus f3 square. And KKLT has one non-perturbative term, which is e to the power of minus rho. So there are square of the fluxes and one non-perturbative term. If you take these two terms, you will not see that there is a problem in hierarchy in this thing. Because there are, what happens is that there are e to the power of minus rho come from the Gaugino condensate.
Yeah.
The same order.
Keshav, I think my question is actually just very conceptual. I'm just saying that, so from your point of view, the point would be that these other terms that you have shown have to be included in order to formulate this as a consistent you know, effective field theory, coming from a consistent effective field theory equation of motion, which KKLT have not done. Is that the statement?
This is also the point of view of Saab-Sethi. Yes. So it turns out that if you take W0 equal to 0, the superpotential not equal to 0, then to the same order, if you take R to the power of 4 term, you have to take all quartic order term in the theory.
Right.
Same order.
No, yeah.
Yeah, but that is unfortunately not been taken in that.
Yeah.
This is the issue I'm having with that solution.
Okay, thank you.
I had a brief question, if I can ask.
Yeah.
You're saying de Sitter is a state, but I thought in our understanding of what quantum gravity should be, there's a vacuum with some fixed boundary conditions, and then every state should have the same asymptotic behavior. So de Sitter is a state in what gravity?
Okay, so de Sitter space is a state in the full theory, of course, in the full M theory.
I know, but with what asymptotic behavior?
Yeah, so the asymptotic behavior. So my understanding is that the vacuum. So first, let me answer your question about the vacuum. The vacuum is Minkowski.
Okay, so de Sitter is a state in Minkowski vacuum gravities.
Yes.
But then, of course, it has different asymptotic behavior.
Yes, asymptotically, it may not exactly. Yeah, that's what is coming out.
So is anti-de Sitter also a state in Minkowski gravity?
I don't think so.
So then maybe does it have to do with the difference between spatial and time boundary conditions, or because right? I mean, just to say what we have always told. If you have a particular like ADS gravity, then an ADS black hole is a state in ADS gravity.
Yes.
And a Minkowski black hole is a state in Minkowski gravity. So always the boundary conditions of the state must match the boundary behavior of the underlying vacuum.
Yeah.
But here you are saying that de Sitter is some kind of state in a flat space, in a Minkowski space-time theory.
Yeah.
Of course, there may be, I don't know if it's a possible argument that, well, being time dependent, somehow what is changing is the future and past behavior, not the spatial infinity behavior.
Yeah.
Is that very important?
That's yeah. So it is exactly the point. Was Saab also? I was talking to him a few days ago. It's exactly the point he was also said.
Has anybody emphasized this point in papers? Is it discussed in your paper in any detail?
Actually, maybe Diwali has done it because he was the first to come up with this idea.
Okay,
we didn't know about it, unfortunately, but he contacted us saying that he thought about it and it should be regarded as his idea. So I would say, but of course, he was talking about 4D de Sitter. We are saying that it's in string theory. Yeah. But one more thing happened. Sorry, if there's another question.
Okay, so 2 questions. Just to see if I understood. In your construction, your coherent state, your de Sitter state, is a solution to 2 derivative gravity, or you need to consider all the higher derivatives?
Higher derivatives, yes.
So it's not a solution or a state in a 2 derivative gravity theory anyway.
It's definitely not a state in a 2 derivative gravity. In fact, the equation of motion satisfied by the coherent state, which looks like a Schwinger-Dyson equation, it turns out that R mu nu minus half G mu nu R, the right-hand side has up to quartic order pieces. All quartic order pieces, R to the power of 4, G to the power of 4.
Okay.
So it is essential.
And a quick question regarding the previous question also.
Yes. I think the audio is gone away.
Shaheen? Okay.
Yeah, he seems to have disappeared. I mean, he's there, but his audio is not hearable.
Working somehow.
Um,
Okay, so I think it has been quite a lot of discussion.
Yeah.
So we will have you again in a conference, and you can ask.
When is the conference?
It's October 19 to 23. So there'll be many speakers on swamp plan, including Tom Rudelius, Wafa himself, Kumrun himself.
Wafa himself is there.
Yeah. Okay, so it was thanks for the great talk again, and thanks for thanks for such a long and nice talk, which is quite nice for us to listen. Yeah. So then have a nice day and see you again next week.
And my regards to everybody who is there, and thanks for coming to my talk. And you can see my book collection.
Yeah, quite impressive. Although we don't know what these books are, we can't see them.
These are graphic novels.
Okay.
Mostly murder.
Yeah.
Okay. So I'm turning the recording off.
Okay.
And
Right.
bye.
So, thank you very much, and good night from my side. And I guess it's
Okay. Bye.
Bye.
Thanks, Ryan. Bye.
Bye.
Bye.